Redox reactions are probably the most important class of chemical reactions that take place in aqueous solutions. Redox reactions is short for oxidation-reduction reactions. And redox reactions involve oxidation processes, which is loss of electrons, and reduction processes, which is gain of electrons. So redox reactions are electron transfer reactions. We saw in the previous video an example of an acid plus a reactive metal as one of the gas-producing chemical reactions in aqueous solutions. Acid plus reactive metal gives you a salt plus hydrogen gas. The example that we used was the acid hydrochloric acid reacting with the metal zinc to produce the salt zinc chloride and elemental hydrogen gas. That's the full ionic equation for this reaction. As you can see, the strong acid, the 2HCl, in the full ionic equation, best represented as separate 2H plus ions and 2Cl minus ions. And the strong electrolyte on the product side, the zinc chloride, best represented as separated zinc 2 plus ions and the 2Cl minus ions. We can see here that the chloride ions on the left-hand side undergo no physical or chemical change compared to on the right-hand side here. So the chloride ions are spectator ions, and we can cancel them out to get the net ionic reaction here, where we've got 2H plus ions reacting with metallic zinc to produce the zinc 2 plus ion plus hydrogen gas. Now what's worth noting here is the change of charge. We start off with zinc metal, which has 0 charge, and after the reaction it has a +2 charge. Prior to the reaction, hydrogen has a +1 charge, and after the reaction it has a 0 charge. So these change of charge actually equate to electron transfer. Species are, in this chemical equation, are losing electrons, and other species are gaining electrons. And often in these redox reactions, the challenge is to find out exactly which one is doing what. So half equations can be used to track electron transfer. So if we looked at this net ionic equation, 2H plus zinc goes to zinc 2 plus H2 gas, we can split it into two halves. We can just focus on what's happening with the zinc, and we can see that the zinc solid is being transformed into zinc 2 plus. The only way it could have done that was to lose 2 electrons. This is said to be the oxidation half reaction. Oxidation is loss of electrons. What I want you to note here in this half equation, we've got 1 zinc on this side and we've got 1 zinc on this side. We have 0 charge overall on this side, and we have a +2 charge associated with the zinc and a 2 minus charge associated with the electrons. So what we've actually got here is mass balance, 1 zinc on each side, and we've got charge balance. We've got net 0 charge on both sides. The zinc has lost 2 electrons to become the zinc 2 plus ion, and that's an oxidation process. And what we've written out here is the oxidation half equation for that process. If we just focus on what happens to the hydrogen, we can see that the 2H plus ions actually end up as the elemental H2 gas. Now, in order for that to happen, hydrogen ions must have accepted electrons or gained electrons. Each one of those hydrogen ions has gained 1 electron each, and the hydrogen H2 molecule has been formed. Again, we can see the half equation here for the conversion of H plus ions to H2 being both mass balance, we've got 2 H's there and we've got 2 H's there, and it's charge balance, we've got a total of 2 plus the 2 minus is 0 on the left hand side, and we've got 0 on the right hand side as well. So half equations are both mass balance and charge balance. We've never had to worry about equations being charge balanced before, but in redox equations it becomes very important. This second equation is the reduction half equation. Reduction means gain of electrons, and the 2 electrons on the left-hand side means that the H plus ions have gained them. If you are confused about oxidation and reduction and what gets lost and what gets gained, this little mnemonic up in the top right-hand corner will help. Oil rig. Oxidation is loss, reduction is gain. Oxidation involves loss of electrons, reduction involves gain of electrons. So the little mnemonic oil rig is always good to help out to avoid that confusion. So let's look at the oxidation half equation in a bit more detail here. When we write oxidation half equations, the electrons are written on the right-hand side to indicate that those electrons have been lost from the zinc. In the reduction half equation, we can see that the electrons are written on the left-hand side. Electrons have been gained. So that's another way of working out whether electrons have been gained or lost and whether you've got oxidation happening or reduction happening. If you see electrons on the right-hand side of a half equation, that's oxidation. If you see electrons on the left-hand side, that's reduction. Now, we can sum up everything on the left-hand side of the arrow in these 2 equations and everything on the right-hand side of the arrow. And when we do that, we'll see that these 2 electrons here will cancel with these 2 electrons here. Adding up everything on the left-hand side of the arrow, we get the 2H plus the Zn solid, and adding everything up on the right-hand side, we get the Zn2 plus H2. And so what we've done is actually regenerated the redox equation. So redox equations are just an arithmetic sum of the respective oxidation and reduction half equations. And you'll notice there that the electrons cancel out and we never have electrons appearing in the redox equation. Should also mention at this stage that oxidation and reduction occur simultaneously, and so you cannot lose these 2 electrons here without them being gained by something else. And that's actually a consequence of the law of conservation of mass. You'll remember that electrons actually do have mass, so you just can't lose that mass. If one substance loses electrons, something else has to gain those electrons. Oxidation and reduction occur simultaneously. Now, another concept that we need to know about when considering redox reactions is oxidizing agents and reducing agents. So an oxidizing agent is a substance that causes the oxidation of another substance. It is itself reduced in a redox process. So let's have a look what that means. If we go back to our redox equation here for the reaction between the acid and reactive metal, we can see here that the 2H plus ions over here have caused the oxidation of zinc to zinc 2 plus. So, and in that process, they have themselves been reduced from H plus ions to the H2 gas. So in this sense, they've caused the oxidation, they are themselves reduced. The H plus ions are the oxidizing agent in this particular reaction here. A reducing agent is a substance that causes the reduction of another substance, and it is itself oxidized in a redox process. So if we go back to our redox equation, acid plus reactive metal, we see that zinc actually causes the reduction of H plus ion, and it is itself oxidized. So in this process, zinc is the reducing agent. You'll always have a reducing agent, you'll always have an oxidizing agent in these redox reactions. So how can we tell if a chemical reaction is in fact actually a redox reaction? All right, because I'm going to tell you that this particular reaction here, the combustion of methane to form carbon dioxide and water, is in fact a redox reaction. And that might surprise you because every substance in this chemical reaction is a molecular substance. There are no ions present and there are no net charges anywhere in this chemical equation. Acid plus base to give salt plus water. These reactions are not redox reactions. They are in fact proton transfer reactions. Acid plus carbonate to give you salt plus carbon dioxide plus water. These are not redox reactions. Again, they're proton transfer reactions. Acid plus sulfite to give salt plus sulfur dioxide plus water. not a redox reaction, again a proton transfer reaction. Yet the acid plus reactive metal reactions are redox reactions. They involve electron transfer, and there's oxidation taking place and reduction taking place. So go back to our question, how can we tell if a chemical reaction is in fact a redox reaction? How can we tell that electron transfer has occurred? How can we identify what the oxidizing agent is, and how can we identify what the reducing agent is? We do this by assigning oxidation numbers to atoms within substances in the chemical equations. If the oxidation number of an atom changes, then that atom has undergone oxidation or reduction. So in the case of our acid plus zinc, we see that we've got a change in oxidation number from 0 to +2 for the zinc, and so we know that zinc has undergone an oxidation or a reduction process. In this case, it's oxidation. And we see that the charge +1 has been reduced to 0, and that means that the H+ ions have undergone a reduction reaction. The oxidation number of an atom in a substance is defined as the actual charge on the atom if it exists as a monatomic ion, so a monatomic ion such as the H+ ion, or we assign a hypothetical charge to the atom in a substance by simple rules. And here are these rules. The oxidation number of elements is always 0. The oxidation number of monatomic ions is the charge on the ion. So the H+ ion, +1. The Cl- ion, -1. The Zn2+ ion, +2, etc., etc. For oxygen-containing compounds, the oxidation number for oxygen is -2 in just about all of its compounds, and the main exception there being hydrogen peroxide, but we'll rarely have to deal with that exception. Similarly, for hydrogen, the oxidation number for hydrogen in its compounds is +1, and there is the very rare exceptions of the metal hydrides, and again, we don't often come across those. The oxidation number of the halogens is -1. Fluorine is always -1. Chlorine, bromine, iodine, they're always -1 as well, except when they're involved in binary compounds with elements of higher electronegativity. So that's elements of oxygen or another halogen above it in the periodic table. And rule number 6 here is very important. The sum of the oxidation numbers of all the atoms in a compound is 0. And so this helps us determine the unknown oxidation number of some atoms in some compounds. And the sum of the oxidation numbers of all the atoms in a polyatomic ion has to equal the charge on the ion. Now these rules are best demonstrated by example. So let's go back to our equation here. We can see that zinc is in the form of elemental zinc. All elements have a oxidation number of 0. Zinc 2+ is a monatomic ion. There's only one atom in that ion, and the charge on that ion is 2+. So the oxidation state, or the oxidation number for zinc 2+ is +2. If the oxidation number of an atom increases, then that atom has undergone oxidation. So zinc going from zinc solid to zinc 2+, we already know it's an oxidation process because we know that can only happen by losing electrons. And now what we can see is this change in oxidation number, where the oxidation number has increased, means that that's an oxidation process. So if we look at the H+ ion, it also is a monatomic ion. So the oxidation number for the H+ ion is its own charge. It's a +1. And elemental hydrogen over here, the oxidation number for all elements is 0. So if the oxidation number of an atom decreases or reduces, that's a good way of remembering it. If the oxidation number reduces, then that atom has undergone reduction. And so the H+ ion has been reduced to elemental hydrogen. So we'll get back to our combustion reaction of methane plus oxygen to produce carbon dioxide plus water. We can identify the element here. Elemental oxygen has an oxidation number of 0, so that's an easy one. We'll look on the left-hand side for some of these other elements. We've got hydrogen. Hydrogen is always +1 in its compounds there, so that was one of the rules. And so from that, because the sum of all the oxidation numbers in a compound has to equal 0, if hydrogen is +1 and there are 4 +1s in the methane molecule, then carbon has to be -4. So we can work that out over here. The unknown oxidation number for carbon plus 4 times the oxidation number for hydrogen, that's 4 times +1, has to equal 0. So the oxidation state for carbon in methane is -4. As we go across to the right-hand side, we can see the oxidation number for oxygen is -2 in all its compounds, with some very rare exceptions. And so we can see that a reduction has taken place. We've gone from 0 to -2. The oxidation number has decreased or reduced, therefore reduction has taken place. Oxygen has undergone reduction. If we look at the hydrogen, we can see that hydrogen started off as +1 on the left-hand side, and it still stays as +1 on the right-hand side. Hydrogen is always +1 in its compounds, with very rare exceptions. The carbon, on the other hand, it started as -4 and it ended up as +4. So how do we work out that carbon is +4 in carbon dioxide? Well, oxygen is -2 and there are 2 oxygen atoms there. That's a total of a -4 charge. The sum of them, of all the atoms in a compound, has to equal 0. So we've got the unknown carbon in carbon dioxide plus 2 times -2, which is the oxidation number for oxygen, has to equal 0. And so carbon in carbon dioxide must have an oxidation number of +4. And so because the oxidation number has increased from -4 up to +4, that is an oxidation process. So oxygen has caused the oxidation of methane. It was itself reduced in that process. It is therefore the oxidizing agent. Conversely, methane, or more particularly the carbon atoms in methane, have caused the reduction of elemental oxygen. The methane was itself oxidized, or at least the carbon atoms in the methane were oxidized, and so methane, or the carbon atoms within the methane, are considered to be the reducing agent.